Hey guys, today we are going to look at Unit 1.1, the nature of science. And specifically, we're going to focus on Part 1 notes, which looks at kind of an intro to science, the scientific method, measurements, etc., all that good stuff. So let's go ahead and get started, shall we? There we go. So first, what is the scientific method? Now, we've all, at this point, a lot of us have heard of it, done it, etc. So we know what it is, but let's kind of define it a little bit. It's a method of procedure that has characterized natural science since the 17th century, consisting of systemic observation, measurement, and experiment, and the formulation, testing, and modification of hypotheses. So what this means is that it is a set procedure that we can use in order to answer questions about the world around us. We notice something in the world, we ask a question about it. This is a set of steps to help us go about trying to find the answer through observation and experimentation. So let's start talking about the different steps. Now, before people start saying, but I learned a different number of steps, that's okay. Different textbooks have them listed differently. Sometimes they condense them down, sometimes they spread them out. It's fine. It's all the same information. So the first thing you have to do is you have to observe something in the world around you. You have to notice something. The sky is blue. Plants are green. Rocks are hard. You have to notice something. And once you notice something, you're going to formulate a question about why that thing occurs. So why is the sky blue? Why are plants green? Why is a rock hard? So now that you have your questions, you're going to do a little bit of research. And what we're trying to do is figure out what is already known. So I can look through this. It gives me background knowledge. It helps me to build a foundation of knowledge for step 4, which is to form your hypotheses. Now, everyone knows what a hypothesis is. I'm hoping by this stage, most of you do. And what it is an educated guess. So it's what do you think will occur? Now, notice what I said though, an educated guess. That means that you have to have some foundational knowledge in order to form your hypothesis. And that's why we do research ahead of time. Now, do we always ask you to do research in a classroom setting? No, because essentially that's what us going through the chapter and doing the notes allows for. It provides you that foundational knowledge instead of you searching it out on your own. See, we do try and help you. All right. Once you have your hypothesis, you are going to come up with an experiment in order to try and prove it. So you're going to go through a series of very carefully controlled tests. What that means is you are going to keep everything the same except for one variable. This way you can test to see if that one variable is the cause of whatever it is. So maybe I want to look at why are plants green? And in my hypothesis, I said that plants are green because they absorb algae from the soil. And what I would do then is I would set up an experiment of having the same kind of plant, but in different soil. That maybe one has just regular soil from outside. That'd be my control group. I would have one with extra algae added to it, one with just a little bit of algae added to it, one that I could try and sift and get like pure just topsoil from like Lowe's or Home Depot. But I would set that up and then I would measure the growth, or not the growth of the plants, but the degree of greenness in the plants. And when I'm doing that, Once I have my experiment set up and I'm running it, that takes us to the next step is observations. I'm going to observe what happens during the experiment. In other words, I'm going to collect data. Whether I collect numerical data or observational data, doesn't matter. You are going to collect data from your experiment at this point. Then once you have your data, you're going to analyze it and then come up with your conclusion. Now, the conclusion may support your hypothesis or it may not support your hypothesis. It's completely fine. Maybe during my algae making plants green experiment, I noticed that no matter what kind of soil, all the plants had the same shade of green. So that tells me that my hypothesis that algae in the soil is what gives plants their green color was not accurate. Because if it was accurate, then the soil with the most algae should make the plant the more green. But if that didn't occur, then it can't be the algae. So my hypothesis was wrong, and that is fine. Scientists typically learn more from wrong hypotheses than they do from right ones. So it's okay if your hypothesis is incorrect. All right, so let's move on now to the variables. So we have a few variables that we're going to mention here. I'm also going to talk about constants. We'll talk about that in a moment. So the control group is your known test group. It's what it would be considered the normal circumstances. So what is a normal circumstance for that experiment? Essentially gives you something to compare your experimental groups to. The independent variable is the variable you are choosing to test. So what are you choosing to do differently in that experiment? That is your independent variable. Your dependent variable will then change in response to your independent variable, which is why it's dependent on what you are changing. So the dependent variable, you can think of it as what are you measuring or what are you observing? What are you looking for in the experiments? What kind of data are you collecting? That's what the dependent variable looks at. And then constants or controlled variables are everything else that you want to keep the same across every experimental group. We'll talk about that with the example. So here's our plant experiment. We are setting up an experiment to see which liquid will help a plant to grow the tallest. The liquids include coffee, water, tea, grape juice, and Pepsi. First thing we have to do is identify the variables. So we'll start with the control variables. I want to test to see how types of liquid affect plant growth. That means if it's not a type of liquid, I want it to be the same among all the plants. So that means I want to use the same type of plant. Actually, let's go. So controlled variables are things you want to keep the same among all groups. So these are what we are not testing. We want to keep the type of plant the same. We don't want to use different types of plants for each group. We want to keep the amount of light the same, whether they get the light from the sun or from lamps. We want to keep the amount of liquid the same. We want to make sure they have the same type of soil, that they're exposed to the same temperature. Because if we start letting these change, then they can also affect the growth of the plants, and then we won't know exactly what is going on. So these are all things we want to keep the same. We call them controlled variables because we're controlling them. We're not letting them be different. A lot of times they can also be called the constants in an experiment. Now the liquids include water, coffee, tea, grape juice, and Pepsi. Which one of those would be our control group? One of them is our control group. One of them is considered normal. Well, let's take a look. The control group is a test group that is kept under known circumstances. And what that means is we know what should happen. So in this experiment, the test group would be water, because we know what will happen if we add water to plants. We know plants grow when you water them. Look outside when it rains. That's how plants get their water. So we know that water should help a plant grow. Now, this is going to give us a good comparison group. We know plants should grow with water, so now we can test all of the other experimental groups, the plants given Pepsi or tea or coffee or grape juice. We can test to see how do they grow in comparison with water. Do they grow better than water? Do they grow worse than water? All right. So my independent variable is, what am I choosing to do differently? Well, let's take a look. So in this experiment, I want to test to see which liquid will help plants grow tallest. So that means that the condition that I am testing, the thing that I am choosing to do differently in each of these groups, would be the type of liquid. So the type of liquid would be my independent variable. I am choosing to give this plant water and that plant coffee and that plant tea, and so on and so on. It is what I am choosing to do differently. So that's why the type of liquid would be my independent variable. Well, now we have dependent variable. What is going to change in response to the type of liquid? In other words, what am I going to measure? So as we said, the dependent changes in response to the independent. It's what am I looking for? What am I measuring? Well, we said in the experiment is to look to see which liquid will help plants grow tallest. So what am I going to measure? How tall they get. So I'm going to measure the height of the plants. And that means that this is going to be my dependent variable. I am looking to see if the type of liquids will cause the plants to grow better or worse. So will they get taller or shorter? Bless you. So that is changing in response to the liquids that I'm giving them. It is what I am measuring. So the height of the plants would be my dependent variable. All right. Talking about observations, there's two categories of observations: qualitative and quantitative. Qualitative is more of a description, something that you can notice. It's not measurable. So this pillow is squishy. It's soft. It's striped. This blanket has different colors. It has blue. It has light blue, dark blue. It has green. This table that the computer is sitting on, it's hard. My shirt is blue. My face is a little shiny right now. Got a little summer sweat going on. Those are all examples of qualitative observations. Those are just things that you can figure out using your five senses. So if I was to taste something and it tastes salty, that's a qualitative observation. If I smell something and it smells sweet, that's qualitative observation. Table is loud when I knock on it versus the couch, which isn't. So these are all just descriptions based on what information you can gather with your five senses. Quantitative measure or observations are measurable, meaning that you're going to use some kind of instrument in order to figure them out. I can measure the mass of the pillow using a scale. If I had a ruler or a yardstick or a meter stick with me, I can measure the length of the computer screen. I can measure the area of the blanket. Let's see, volume inside the pillow or the volume inside this cup. I can measure all of those and give an objective answer. So what objective means is that there's really only one answer. You're not going to have two people measure the inside volume of this cup and get two things that are way different. One person is not going to come up with 5 milliliters, and the other person is not going to come up with 500 milliliters, as opposed to qualitative, which is more subjective. So maybe I think this blanket is softer than the couch. Maybe my husband thinks the couch is softer than the blanket. We can both agree they're soft, but we're not necessarily going to agree on which is the softest. So it's more subjective with qualitative and more objective with quantitative. Speaking about measurements, what we use is the SI units of measurements. So it's the International System of Measurements, or the International System. The reason why it's SI is because the original terminology is in French. Bear with me. I do not speak French. It's like Système Internationale. I'm probably saying that wrong. Again, I do not speak French. And it's based on the metric system, which is really nice because when you want to convert between the different increments in the metric system, you always increase or decrease by multiples of 10, which means all you're really doing is moving the decimal point around. We also have something called derived units, which are a combination of base units. So meter is just a regular base unit. It measures length. Second is a regular base unit. It measures time. But if we talk about something in terms of meters per second, so maybe it's speed or velocity, now it's a derived unit. Now it's a combination of base units. It is meters per second. We have two different base units involved. So that's what we mean by a derived unit. All right. So here are some examples of small measurements, specifically the prefixes. You always start off with a base unit like meters, but then you can talk about smaller versions of it by adding one of these prefixes to it. So a decimeter is 1/10 the size of a meter. So if this is a meter, a decimeter would be 1/10 that size. And centi would be 1/100th the size of a meter. So again, if this is a meter, then that's a centimeter. And a millimeter would be 1/1000th the size of a meter. So again, if this is a meter, tiny thing, that's a millimeter. So since these all kind of increase 10th, 100th, 1000th, we can go meter, decimeter, centimeter, millimeter. Not too bad. I have a whole video on conversions between these. Then we have some large ones. I gave just kind of some of the more common large ones. There are other prefixes in between these, but these are 3 more common larger measurements. So kilo is 1,000 times bigger than the base unit. So a kilometer can hold 1,000 meters in it. A megameter means that it's 1,000,000 times bigger. 1 megameter is equal to 1,000,000 meters. And a giga, which means billion, a gigameter would be the equivalent of 1 gigameter equaling 1 billion meters. So notice we're just kind of adding zeros to different locations. We're not changing the values as opposed to the empiric system that we use here in the US. So this is just kind of showing you a bit of the scale. Again, you can kind of look at these more in a video where we look at basic conversions between the base units and then 3 above, 3 below. So we start with our base unit, deca, hecto, kilo, deci, centi, milli as the small side. This also just shows you some of the others that are commonly used for small. We have micro, nano, and pico. But at the end of this presentation, I have a link to one of my videos, also other videos that show you and kind of walk you through how to do the conversion. So I hope those help. Again, just kind of talking about the prefixes and then what they mean in terms of how they relate to the base unit. Notice just adding the zeros. We're moving the decimal point around. That's all we're doing. Scientific notation, we're not going to get into a whole lot in this particular presentation because it's really better to show you, and I do have a link to a video that discusses how to do scientific notation. Essentially, it's a way to write really big or really small numbers, and how we do it is we simplify it by moving the decimal point, so there's only one non-zero numeral in front of it, and then we put that number times 10 to the exponent. The exponent is the number of places you move the decimal point. So this is kind of showing it in both ways. Let's start with this number. We have 2 billion. And if I want to simplify it, I can move the decimal point from the end. You don't see it there. When you don't see it, it's assumed to be at the end, 2 behind the 2. So to do that, I'm going to move it 1, 2, 3, 4, 5, 6, 7, 8, 9, and that's how they get 2 times 10 to the 9th. Again, it's harder to show it this way just by describing it. I do have a link to videos that show how to actually do it. And I definitely recommend you checking those out. Law versus theory. Law we can kind of all really agree on. It's a summary of many experimental results and observations. It tells how things work. In other words, what will happen. Because it tells what will happen, we can agree that they've been proven to be true. If I throw this up, what will happen? It will fall back down. So it tells me how things work. Something's up high, it'll come back down. Theory, on the other hand, is an explanation of some phenomenon that is based on observation, experimentation, and reasoning. It tells us why something happened. Now, it's really, really, really difficult to prove the why of something, which is why we say that theories cannot 100% be proven. However, they are very highly supported by mountains and mountains of data, evidence, experiments, etc. So when scientists talk about theory, they don't use it the same way that it's used in common society. A lot of times when you hear people on TV, they say, oh yeah, I have a theory about that. What they mean is they have an educated guess. In other words, they're using the word theory like we scientists use the word hypothesis. When a scientist talks about a theory, they're saying, I have an explanation for why something occurs based on a lot of data, observation, experimentation, research, etc. And to give you an example, gravity. There's both the law of gravity and the theory of gravity. They both exist. So the law of theory tells us what will happen. And very simply put, well, what will happen? What goes up must come back down. I throw something up, it comes back down. That's the law of gravity. It tells me what will occur if I throw something in the air. It will come back down. The theory of gravity explains why the neck pillow comes back down. Because a mass of an object becomes, when it becomes large enough, such as the moon or a planet, it generates this invisible field around it that creates an attractive force to objects, other objects that also have mass. The Earth is a large body. It has a really, really large mass, and that large mass allows it to generate this invisible field around it. When another object with mass enters that field, then the attractive force of the field pulls it down to the Earth's surface. Now, can I show you this invisible field? No. But that doesn't mean that we can't measure it. We can't observe what happens within it. We can't figure out and do research and experimentation that supports the theory of gravity. But since I cannot show you this invisible force field, I can't actually 100% prove it, no matter how much data I have that supports this theory. So that's kind of the difference between those. All right, mottos. So a motto is any representation used to understand an object or event. So pretty much anything that helps you to understand something better is considered a motto. A lot of times when we talk about mottos, we think of them like this one with the eye, how it's this physical shape, this physical structure that we can look at. But that's not always the case. Yes, there are some like that. Like with this eye, it's going to be an enlarged version of the eye so you can see the details within it. There's similar 3D models of the solar system that are much smaller to help us get an idea of what is in our solar system. But we can also use drawings on paper or with computers like this model over here beneath my wonderful video face of a molecule. So the different colors represent different elements, and this is showing us how these atoms come together to form this structure. They can be computer simulation models like this one here. So by looking at this, I know if I was just to tell you that it's measuring temperature, we can figure out that the red and yellow and orangey in the middle means that that is a warmer water temperature. The green, still kind of warm, but then we notice it gets darker and blue and purple on the outside. That means it's cooling down. I can look at this and I can understand that the water tends to be warmer around the middle of near the equator, but then as it moves farther closer to the poles, farther away from the equator, closer to the poles, it gets cooler. So it helps me to understand that. Graphs help us to understand data that's been collected. So any of these would be considered models. All right, speaking about graphs, graphs are simply visual ways to display and analyze data. So they help me to quickly understand what's going on. Three main types used that we're going to discuss are line graphs, bar graphs, and pie charts. Start with line graphs first. This is really good for showing continuous change over time. So a lot of times we'll have the year at the bottom, the time, and then what we're counting on the side. Now what does that mean? The x-axis is the horizontal one at the bottom. And a lot of times we'll put the independent variable there. And before you start saying, but Ms. Komar, how do we change time? We can't change it. I'll explain why in a moment. Let me finish talking about how this is set up. The y-axis, that's the vertical one on the side, that's the dependent variable. That's what we're measuring. Now in this particular graph, they're looking at the number of dolphins seen in Santa Barbara Channel between 1996 and 2001. So I am choosing to count the number of dolphins each year. That's why time can be an independent variable, because I'm choosing the time frames that I'm looking at. I'm choosing to go out in each year, 1996, 97, 98, 99, 2000, 2001. I'm choosing to go out and count the number of dolphins. That's why time can be an independent variable. And what am I measuring? The number of dolphins. So that's why that is the independent variable. Now, just telling you that I counted the number of dolphins each year, even without looking at the actual numbers and data, I can tell you what happened. So the population started off very low, then it shot up. It got, within 1 year, it got super big. Then it kind of went down, up a little bit, and then it increased at the end. So I can look at this and I can understand that. I don't even have to see the numbers to know what's going on. Start off low, massive increase, then we had a dip, went up a little bit, down a little bit, increased again. So again, it's just a really easy way for me to see this continual change in the dolphin population over time. Let's talk about bar and pie charts. So both of these kind of show similar data. They're both used for comparing and comparisons. They just do it in a different way. Bar graphs will compare items using the actual data. So the actual measurements are what you will use for a bar graph. So here we have the example, favorite color in the class, or of individuals in the class. 4 kids, their favorite color is yellow. 5 kids like red the best. 6 kids like blue the best. 1 likes green the best. 4 like pink the best. So those are my actual measurements, and I put them in the bar graph. But pie charts, generally we show it not as the full actual measurements, but we show it as percentages. So a lot of times when someone does a bar graph, they'll do a similar pie chart to go along with it. Now, this isn't exactly the same because this is looking at favorite type of movie. But it's the same idea. I could take these actual numbers, figure out their percentages, and then turn them into a pie chart. Now for this one, the type of movies, it's showing me both the actual data, but the pie slice itself is a result of the percentage. So in this graph, the pie chart, favorite type of movie, 4 kids like or sci-fi the best, that's 20%. 4 like comedy the best, that's 20%. 5 like action, that is 25%. 6 like romance, that's 30%. And 1 likes drama, that is 5%. So again, we can kind of see this. And actually, these are all the same numbers, just different colors as opposed to this. So yeah. Nope, that is not what I meant to do. Nope, nope, nope. Let's get back to this. There we go. Sorry about that. All right. So, good? Yeah. All right. Now that's all that's really left is talk about the additional resources. Got lots of them for you. First, we have my Science in Pajamas videos. Have one on the scientific method where we go through the steps using an example. I'm not going to have you watch it now. We have one on experimental variables. And again, using an example to talk about the different variables, what they are. Have one showing you how to do metric conversions. So definitely check that one out if you're not sure. And we also have one on how to do scientific notation. Again, if you still need some help with that, definitely check that video out. And so I'm not just shamelessly self-promoting myself. I do have a whole bunch of videos from other sources. There's a Khan Academy on scientific method, Amoeba Sisters on the nature of science, Amoeba Sisters on law and theory, Brainstem on metric conversions, Organic Chemistry Tutor on scientific notation, Amoeba Sisters on lab safety, SMS Phys Science on quantitative versus qualitative observations, and Bozeman Science Beginner's Guide to Graphing Data. Now, I'm not going to go through all these. I just wanted you to know about them so that you are able to have access to them. Now, yes, you can't access them while watching this video, but I will post a link for the actual Prezi presentation in the description so that you can go to the Prezi and access the videos from there. But I hope this was informative. I hope this helped to explain some of the nuances of scientific method and all that good stuff. And if you have any questions, definitely hit me up in class or email or through our Google Classroom. In the meantime, you guys, stay safe, stay healthy.